Okay, so let's take a look at this. Okay, so we have 3 particulate diagram sets on the right. And what we need to do is answer the questions. Let me make sure you can see the screen. Okay. So first of all, which of the following represents a complete reaction? Okay, so the first thing is just to make sure you understand how this is written. So remember, the left side is going to be like your initial conditions, how you start off, and this is kind of your final conditions on the right. Okay, so if the reaction goes to completion, that means what you're going to end up with is all AB on the left and no AB on the right. So you're looking for the picture that has no combined blue and red. Okay, so if I look at the pictures, the 3 pictures, I see that number 1 looks good. It has no blue and red together. So this looks like it completely broke apart to A plus B. Just look through the second one. Second one looks like it's a mixture of AB and A and B. And number 3 also looks the same. These two look kind of similar. They both have reactant and product in them. So my answer for number 1 the only choice would be 1. Okay. Number 1 goes to completion. Okay. And I also just want to point out for particulate diagrams, in case it's not an equilibrium one, or this type, I want you, if you count the total number of particles, you'll see that the particles on the left are the same number as the particles at the right, whether they're separated or together. Okay, that's important to recognize. Okay, so which represents equilibrium? Okay, well, that's a little tricky. Okay, I look here in this picture and I say, okay, I could count my particles. It looks like I have 1, 2, 3, 4, 5 product particles, and it looks like I have 2 of each reactant particle. Okay, in this one, it looks like it's a more evenly spread. I have 3, I'm sorry, I think I flipped what I said. Excuse me, I have 5 reactant particles and 4 product particles. In this one, I have it more evenly spread. I have 3 reactants, and I have basically 4 of each product. Okay, but if you look between the initial and the final, the total number is still the same. So for number 2, which could represent equilibrium, I would say either 2 or 3 could be at equilibrium. And the reason I don't know which one is because I don't know the K value. Okay. The K value is going to tell us a lot. Okay, so for question 3, which would have the largest K equilibrium value? Okay, what we learned yesterday, which was a review from honors, hopefully those that weren't here watched the video, is that K equilibrium is going to equal the concentration of the products raised to their coefficient over reactants. Okay, it's kind of the generic formula. And remember, you don't ever include solids or liquids in that expression. Okay, so remember, if K equilibrium is greater than 1, that means the products are favored. Okay, think about the math there. More products than reactants. That's what that means. If the K equilibrium is less than 1, that would mean that you would have a big denominator, right? If R is greater than P, you would have a fraction, which would be less than 1. That would be reactant favored. Okay, so the one with more product would be the one with the largest equilibrium value. And that would be number 2. I'm sorry, I'm looking at the wrong one. Keep thinking AB is my product, so let me correct myself. AB is my reactant. Number 2 has more reactant than product. Okay, so that would have the smallest equilibrium value. So this, the answer would be number 2. Okay. I have more reactant. Keep thinking of the combined one as my product. That's why I keep misspeaking. Okay, but I have more reactant here than product. So number 2 would have the smallest K value. The largest would be the one with more product. Okay, and if I circle the product, okay, that would be number 3. Okay, so it's important to understand what the K value can tell you, okay, and what equilibrium could look like on a particulate level. Any questions? Okay. So there's one more thing I want to say about the K value, just so you can understand the magnitude of it. We're going to go through this a little bit later in later units, but since we're talking about the magnitude of K, I want to put something up that I do want you to write down. Okay. For K, okay, remember we talked about this yesterday. If K is greater than 1, okay, we know that it's products favored. Right? That means the concentration of the products is going to be greater than the reactants. If K is less than 1, we know that it's going to be reactant favored. Okay, and you can look at the formula to understand why, which means the reactants concentrations are going to be greater than the products. Okay, if K equals 1, basically concentration of the reactants equals the concentration of the products. Okay, but I want to put out a number so that you can understand when to judge whether reaction it would be in equilibrium at all. Okay, so if your K value is extremely large, okay, this is what I want you to recognize. By extremely large, I mean greater than 1,000. Okay, if your K value is greater than 1,000, that pretty much is telling you the reaction is going to completion. Meaning it's not really equilibrium. It's, for our purposes, it's complete products. Okay? So the reaction would go to completion. If the K value is less than 10 thousandths, okay? Okay, it basically means the reaction the forward reaction does not take place. It doesn't proceed at all. Okay, so I just wanted to point out some magnitude numbers of K so that you could recognize when you shift from equilibrium to reaction going to completion, or when you shift from equilibrium to the forward reaction doesn't even take place. Okay, so I'll give you a minute to write that down, and we'll start with the lesson.